In this section, we'll start to look at the equivalence of the NFA and the DFA. That is, we already have hinted earlier that NFA does not give any extra power than a DFA in terms of a computing power. So, equivalence of machines for an automata, whether DFA or an NFA, we say that two machines are equivalent M1 and M2 if the language accepted by the two machines are the same. That is, any string accepted by M1 in the language L of M1 is accepted by M2, and that string is also in language L of M2. So it is both cases, both the machines are equivalent. We have seen an example before of an NFA. This is an NFA where all the transitions are not defined for Q1. So this is an underlying NFA, but the language it accepts is 1, 0, any number of times. So it is 1, 0 asterisk. And we gave a DFA as an example earlier for the same example, where it also accepts 1, 0, any number of times, and it is completely defined as a DFA for all transitions, and all transitions are uniquely defined. So there's only one transition for every state on every input alphabet. So this is a DFA. Even though there are more complications that we can give for NFA, lambda transitions and multiple transitions, but for this example, this DFA also accepts 1, 0 asterisk. So these two machines M1 and M2 are equivalent. So we will prove that the language accepted by the NFAs will also be accepted by the DFAs. Earlier we have indicated a class of languages called regular languages as accepted by an underlying DFA. Now we will say expand it to both the NFAs and the DFAs, and that regular languages are accepted by an NFA as well as by a DFA, and the same computational power. So given an NFA, we can convert it to an equivalent DFA which accepts the same languages. To show that NFA and DFA are equivalent, one way is actually straightforward, because every NFA is accepted by the DFA, because the DFA is trivially an NFA without any extra lambda transitions or multiple transitions on the same input symbol. So any language L that is accepted by DFA is accepted by the NFA. The complication comes the other way around. To show that every language that is accepted by the NFA is accepted by a DFA, which is a regular language. So the proof in this aspect will convert an NFA to an equivalent DFA, so that any language accepted by the NFA is also accepted by the DFA. I think the way that we said here are two terms, proof and also converted. So that is, this step we will prove it by construction, proof by construction. And the constructive process is to give a methodology to convert an NFA to an equivalent DFA. So given this particular NFA, we'll construct M prime, which is a equivalent DFA, so that they accept the same language. So language accepted by this machine M will also be accepted by the underlying the language accepted by the constructed DFA M prime. So this is a procedure or a process, a proof by construction to do the construction from an NFA to a DFA. So we know what is the starting state of the NFA. That's a Q0. So our construction process would be initial state of a DFA is Q0 as a set. So by this conversion of the construction process, a state that is constructed in the underlying DFA will always be some sort of a subset of all the states of the underlying NFA. So to begin with, this is a subset or a set of only one state, a subset of Q which is only one state, which is a set Q0. And then the step 2 would be to convert the NFA by giving all the possible transitions. So for every state in the DFA, which we said is some sort of a subset of the states of Q. So for example, in this case, assume that these are the states in a DFA. So we are trying to come up with the transition function for the DFA from this state of a DFA on an input symbol A, which would be to compute all the underlying possibilities. Where can I end up from a transition from Qi on a symbol A? Where can I end up in a possible transition from Qj to A? So all possible state transitions on this symbol A, and this becomes the new set of states of the underlying NFA, and we'll call it as a state in the constructed DFA. So the DFA construction process is to construct states where each state is defining all possible transitions from a state to on an input symbol A. So the next step, we say it is a repeat the process of step 2. That is, it is an iterative process. So for all the symbols in the alphabet, keep repeating until no more transitions are attached. That is, for every state, for every input symbol, create a new state, and do repeat the same process for the new state created for every symbol, and keep repeating it iteratively till you form all the states and no more states are added or no more transitions are added. So we have now figured out all the states of the underlying DFA, where each state of a DFA represents some sort of a subset of the states of the underlying NFA. So in this step, if a state is a accepting state in the NFA, and if this state belongs to a particular set of that identifies a state in the DFA, we call it as the final state of the DFA. That is, this particular state will make this particular state as a state of the DFA, final state of the DFA. And if lambda is the language accepted by the NFA, which is a null string, then your initial state Q0 also becomes a final state. That is, you accept the null string on the DFA. So the NFA states Q0, Q1, Q2 and all of them that belong to your set of states in Q, the DFA will be some number of states in the power set of Q. So it could be an empty set, or it could be a set with only one state, or a set with many number of states, and so on. So there are multiple possibilities of states of the in the underlying the constructed DFA, but each particular state of the underlying DFA will represent the possibilities that exist in transition in the underlying NFA. Let's make it more clear with an example. So if this is the underlying the NFA that we are trying to construct the DFA. So there are three states in the NFA, Q0, Q1 and Q2. So to be more formal, you can start writing down too if you want to. Q is Q0, Q1 and Q2. The alphabet symbols are A and B. So the starting step of the step 1 would be, what is my state of the underlying DFA, that we call it as the initial state, right? So initial state in the NFA is Q0. So my initial set that I create will be Q0 as a one state set, which becomes the initial state of the DFA, M prime. And then go on to do all the other transitions. So where will I end up on Q0 on an A? The possibilities are, I can end up in Q1 by the extended transition function, and we can make the lambda transition to Q2. So both Q1 and Q2 are possible states that I end up with from Q0 on an A. So I created now a new state called in a DFA Q1, Q2. And then it is a repetitive process, iterative process. So Q0 on a B is not defined, so it is ends up in a set which is our empty set. So this becomes our dead state 2 in this example, and define all the transitions from this new state that we created. So what is Q1 on an A? So we're always looking to underlying NFA and then defining the transitions. So Q1 on an A would be, I can end up in Q1, or I can also make a lambda transition to Q2. So Q1 on an A would be Q1, Q2. And Q2 on an A is not defined. So you end up in the same state now, Q1, Q2. How about Q1, Q2 on a B? So I end up going back to Q0. So from the null set on an A and a B, you remain in the same set. So we define all possible transitions here in the underlying DFA, and these transitions are reflecting the transitions in the underlying NFA. So we end this process if we make sure that there are no new states that are formed in this process. And as you see in the algorithm, step 3 would be to find out what are the final states. The underlying NFA has one state Q1 belong to the final state. So any possible sets of the states here in the underlying DFA that contains Q1 becomes a final state. So in this case, this is the only state because Q1 belongs to this set, and this set becomes the final state, and so you draw the make it the final state. So by the construction process itself, so any possible choices that exist in an NFA, right? So for example, we said Q0 on an A can be in either Q1 or Q2 is explicitly captured by creating a state in the DFA. So all possible choices in the underlying NFA are captured as unique choices in the DFA. So this becomes deterministic and is always equivalent to what is the transitions defined in the NFA. So by the process of construction, so if there exists a walk, a path on any particular string from a state Q0, let's say the initial state Q0 to a state of Qj, then we define transitions in the constructed DFA from this set, initial state set Q0, to a state that includes Qj. So possible choice from Q0 to Qj is explicitly captured as a unique choice by constructing a state with Qj in that set. So the walk exists from Q0 to this state on the same string W in the DFA M prime. So we are mimicking the path or the walk in M prime, very similar to the way that the path existed in the NFA. So if Qj becomes is the final state in the NFA given, then we say that this becomes the final state of the constructed DFA M prime. So if W is accepted by virtue of Qj being a final state, then W is accepted in the DFA by virtue of making this the final state. So thus any string accepted by the NFA M is also accepted by the DFA constructed M prime. So this constructive proof shows that it is equivalent from an NFA to a DFA. So we'll state that as a theorem. So given an NFA, you apply the procedure to construct the M prime, the DFA, and then both of them are equivalent. L of M is the same thing as L of M prime, and if W is accepted by Lm, then W is also accepted by L of M prime. So they're equivalent. Another example, this is straight out of the textbook. So given this NFA M, so now we need you to practice writing it in this fashion quickly. So we are trying to construct the equivalent M prime DFA, right? And the process of writing, just to distinguish between the transitions of two machines N and M and M prime, we refer to the transitions in the NFA being as delta N, the transitions in the DFA being delta D. So just so that you don't get confused in the defining the transition functions delta. So to begin with, as I said, make this the starting state as the starting state set of the initial states, which in this case is Q0, and then iteratively define all possible states. So what happens from in the deterministic DFA that we are trying to construct, delta D of Q0 on a 0, by looking at the corresponding moves of the underlying NFA. So for the Qn, so look for all possibilities of this set Q0 on a 0. I can be in Q0 or in Q1. So this set becomes Q0 Q1. How about Q0 on a 1? So look to the underlying transitions on a NFA. Q0 on a 1 is Q1. So this becomes a state in the DFA. So you're automatically starting with this state Q0 We have defined two new states to begin with, and then iteratively complete all the other transitions. What happens for Q0, Q1 on a 0? Now you need to look for underlying NFA for Q0 on a 0 and Q1 on a 0, and then combine all possibilities, union. So it will be this. Similarly, Q0, complete all the transitions for Q0, Q1, Q2, and keep going. So it's an exhaustive iterative process where you keep defining for all the states that you have come up with as the possible states, all possible transitions for all input symbols have to be defined. And after this, there were no new states that are formed. All the states that you have formed, the transitions have already been defined. So now capture all this transition delta D into a DFA. So the corresponding DFA will have these states that are the subset of the states of the underlying NFA, and all transitions defined in this fashion. So this is a DFA, and it is equivalent to the NFA, because by process of construction, if something is accepted in the NFA, we accept in the DFA. So by the way, the final state should be any state set that includes Q1 as a state. So this is the final state, this is the final state, Q0, Q1, Q2 is the final state, Q1, Q2 is the final state, and none of the other states are final states. So this is an equivalent DFA for the NFA. So start practicing. So any number of problems can be done in this fashion. And I expect you to easily do it on with pen and paper to go through this exhaustive process.